Hello everybody. So now we're going to start with the first example that we will apply on the analytical solution of the equations of motion. And as you see here, I put in the right the steps, and I already highlight the steps that we are going through right now. What I'm going to do now is I'm going to read the whole problem statement, and I'll try to make sure that we understand the geometry and the whatever is going on here, and then we can start with the setting up the or writing the assumptions and the boundary conditions, and then going through the rest of the steps. So this is problem is stating that we have steady incompressible laminar flow, and you need to pay attention to the details because there are a lot of information that need to be translated into proper assumptions. Of a Newtonian fluid in a narrow gap between two infinite parallel plates. So these are the two plates that we see here, and this is the fluid that is flowing between these two plates. It said that the top plate is moving with a velocity u node, and the bottom plate is stationary. So this is fixed plate, this is a moving plate. The distance between these two plates is h, which is this. And keep in mind that this is important, the coordinates that you have here on the figure. So it gives you the coordinate y and x coordinates. And it says that the gravity acts in the negative z direction, and between brackets it says into the page according to the figure. So it's kind of hard to imagine this from the figure that we have here. That's why I made a 3D diagram for it, just to make it easy for you to imagine. So this is xy. So this is these are the two plates. This is the fixed plate. This is the plate that is moving with velocity u node. And the plane that we were looking at is xy plane, which is this. So we are looking from the top. So if you're looking from the top, you would see that this is the top plate that is moving, and this is the fixed plate, and this is the space between them, that's h. And the gravity is acting downward, so it's acting in the negative z direction. So if you're looking from the top, or you're looking at from the top view, then it's going to be into the page. Okay, so if we go back based on this, we are looking at from the top, and then the gravity is acting inside the page. Okay, or into the page. Yeah. The pressure at z equals 0 is P node. So the pressure at z equals 0, let's say this is z equals 0, so this is at this plane, the pressure is P node. And there is no applied pressure other than the hydrostatic pressure due to gravity. And this is an important information. It means that the only source of pressure is the fluid head. So there is no external pressure, it's only the fluid head. And there is no flow in the z direction, so despite the gravity, the fluid is only flowing in one direction, which is what we will see here. We want to derive formulas for the velocity and pressure fields, and when we say velocity and pressure fields, we mean the velocity profile and the pressure profile, or the velocity and the pressure as a function of the system variables, and estimate the shear force per unit area, which is the shear stress acting on the bottom plate. So we need to first write the assumptions based on what we understand from the problem statement. So first, remember the assumptions that we mentioned before that must be there. There must be assumptions that relate to the Navier-Stokes equation, which are already here. It's the Newtonian fluid and incompressible flow with constant properties. It didn't mention that it's constant properties, but we have to assume it. So Navier-Stokes equation is valid. It says that it's steady flow, and steady flow means that any change with time is going to be 0. It also says that it's two infinite parallel plates, and if we try to understand what we mean by these infinite parallel plates, it means that the plates are very large in size. So we can consider this as an indication that there is one dimension that's not affecting the flow. So as we see here, the flow will be in the x direction based on this, and it's affected by the distance. This is the kind of the common sense. It's affected by the distance because the velocity here is 0 and here it has a value, so it varies between here and there. So the third dimension is not affecting. This is what we mean. So it's two-dimensional flow, so any change with z is equal to 0. It also says that it's laminar flow. It didn't explicitly say that it's a parallel flow, but we can assume that it's a parallel flow, meaning that the velocity has only one direction, or one component. So it will be the x component, there is no y component, and it said that there is no flow in z direction, so there is no z component. So the velocity in y and z directions are all zeros. It says that so I just want you to consider these four assumptions. You'd see that these four assumptions are mainly got from the first two lines, or almost the first line. So that's why you need to be careful with reading the problem statement and translating what you understand from the problem statement into proper equations. It says that the gravity acts in the negative z direction, which means that there is no gravity in x and there is no gravity in y directions. And the gravity in z direction is equal to negative g because it's acting in the negative z direction. And the fluid is not flowing due to the pressure gradient. It means that there's no change in pressure with respect to x and with respect to y. And I put them as two parts, and I think this is what the textbook was doing, so I followed what the textbook was doing, but it said the fluid is not flowing due to pressure gradient. The flow is in the x direction, so there is no pressure gradient in x direction, and it also mentioned that there is no applied pressure other than the hydrostatic pressure, so at any value of y at the same height, the value of y at any value of y, the pressure will be the same. It means that this plane is exposed to the same pressure. So we can take these two as a result of this assumption. Anyway, so this is what we can get from the problem statement. Now we can also write the boundary conditions. So the boundary conditions have to do with the boundaries. So we know both conditions will have to do with the no slip boundary condition. So the velocity at the bottom plate is 0. The velocity of the top plate is u naught. So we can say that at y equals 0, ux is 0. At y equals h, ux is u naught. And we know for the pressure that at z equals 0, p equals p naught. So this is what we can get from the problem statement. Now we are done finally with these two parts, and now we can move to the next part, which is simplifying the differential equation. So we said that the velocity in y direction is 0, the velocity in z direction is 0, so this will cancel these two terms, and then the equation will end up like this, which is the derivative of the velocity in x direction with respect to x is 0. So this doesn't mean that the velocity is constant, and this is something you need to be careful when you deal with these equations. These are partial differential equations. It means that the velocity can be dependent on x, y, z, and time. We know that there is no effect of time is because it's steady flow. So we still have three dimensions. The velocity can vary with x, y, and z. So if du by dx is 0, it means that it doesn't mean that the velocity is constant, but it means that the velocity is not dependent on x. Okay, so ux is not function of x. Ux still can be a function of y and z, and we said in the assumptions that it's two-dimensional flow, so there is no effect of z on the velocity. So the velocity is only going to be function of y. Okay, so be careful. This is not an ordinary differential equation. This is a partial differential equation. So if the partial ux partial x is 0, doesn't mean that ux is 0. It means that ux is not dependent on x. Now for the x component of Navier-Stokes equation, what we're going to do is we will cancel some terms. So we know that steady flow, so this is 0. We know that partial ux, partial x is 0 from here, so this is 0. Partial uy is 0 and uz is 0, so these two will be zeros. From the assumptions we knew that partial px, partial x is 0. We know that gx is 0. We know that this is not 0 because or this is 0. This is partial x squared is 0. Ux is function of y, so this will have a value, we cannot cancel this. And we know that ux is not function of z, so this is 0. So the equation will reduce to the second derivative of ux with respect to y is equal to 0. So this is what we're getting from this equation. And you can see now the equations are getting very, very simplified because we deal with very, very simplified cases. Okay, for the y component, we will do the same. There is no effect of time. uy is 0, so these three terms would be zeros. Partial p, partial y is 0, gy is 0, uy is 0, so these three derivative would be 0. So the equation is 0 equal to 0, so we're not getting any new information from this equation. Okay, and this is fine. You can have an equation that's not adding anything new. For the z component, we have the velocity in z direction is 0, so this will cancel all these terms and all these terms. We still have pressure change with z because of the hydrostatic pressure, and we have gz, which is negative g. Okay, so this is the equation that we will have. So we now have the simplified forms of the differential equations, and the next step is to integrate the equations and apply the boundary condition. So this is the equation that we have. If we integrate it twice, it's going to be c1y plus c2, so it's a linear relation. And we can recall the boundary conditions that at y equals 0, u is 0. So if you substitute with 0 and 0, then c2 is 0. And at ux is equal to u node at x equals h. So this is u node is c1 times h, so c1 is u node over h, and now we can substitute in the equation and we get the formula for ux, which is u node over h times y. So this is what we can call the velocity field equation, which we wanted to get from the beginning. Now for the pressure field equation, we can integrate the z component equation, which is dp by dz equals negative g rho g, and it's simple. We can integrate it once. It's going to be p equals negative rho gz plus c3, and we know that at p equals p equals p node at z equals 0, so this makes that c3 is p node, and now p equals p node minus rho g z. Okay, and by the way, this equation is the same equation we used to see before in chapter 3 for the hydrostatic pressure, but we used to see this as p plus rho g z, and this is not different because z in our case is going to be negative because it's going in the negative z direction. So this negative will cancel this negative, and it's going to be plus rho g z. So it's the same equation. Okay. If we want to get the shear stress at the bottom plate, we know that it's a Newtonian fluid, so it's going to be tau equals mu times du by dy. And du by dy is u node over h. So this is the shear stress. So it's going to be the same for all values of y. It's not only for the bottom plate. This is valid for the all values of y. So it's tau equals mu times u node over h. So this is all what we can what we need from this. There is one nice thing that we can do here is we can produce some graphs to kind of see how the parameters affect the system. So I generated one here, and I think this is a nice thing to see, that we have here on the x-axis the velocity, and the y-axis is the horizontal distance, which is y. And I changed here the value of u node, and you see here this relation is linear. Okay, so for different values of u node, starting from 0, that both plates are stationary, then the velocity is going to be 0 everywhere, and up to 2 meters per second, I put different values, and you see the velocity is linear for all of them. So you can see how the velocity is changing, and from this, and this is what we mean, and this is the reason I'm doing this, that we need to understand what we mean by the velocity field equation or the velocity profile. It's an equation that you can apply with or substitute with any value of y to calculate the corresponding value of x. So I can now tell for let's say the u node of 1.5, I can tell at any distance from the bottom plate, let's say at 2.5 centimeters, for instance. Of course, this is not meter, this is centimeter, I think. This is times 10 power minus 3, so it's 2.5 times 10 power minus 3, which is 2.5 millimeters. Okay, so I can tell at 2.5 millimeters that the velocity is going to be 0.7 something. Okay, so this is why we do this. So it's not specifically for one point. It's valid for any point between in the velocity field between the bottom plate and the top plate. So this is the first question, or the first problem. So I'm going to stop here, and we are going to continue next video, inshallah, with another example. So I see you then.